Welcome to The Explainer. We are diving right into something truly mind-bending today. I want you to just imagine for a second that there's this single invisible mathematical glitch. It's like a tiny point of friction that secretly connects the absolute biggest problems across modern tech and medicine. I mean, from the AI programs you're using on your phone every day, all the way to the development of life-saving drugs in global labs, there is a fundamental bug in how we translate perfect math into our physical reality. But, and here's the really great news, 4 incredible brand new breakthroughs have literally just figured out how to fix it. So let's dive into this.
Okay, we have all seen this happen. You're using a state-of-the-art AI image generator, right? You ask it for this beautiful landscape or maybe a photorealistic portrait. The AI starts out perfectly, and then, completely out of nowhere, it just hallucinates. The background melts, the person suddenly has, 6 fingers, or the whole image just collapses into this chaotic glitch. Have you ever actually stopped to wonder why a multi-million-dollar supercomputer suddenly forgets how reality works?
Now, hold that thought and let's jump over to something that seems completely unrelated. Medicine. Have you ever wondered why life-saving clinical trials take so agonizingly long to finish? Even when doctors see amazing early results from, say, a new cancer drug, they usually can't just stop the trial and give it to everyone. They have to wait, sometimes for years, locked into these incredibly rigid schedules. It costs billions of dollars and, honestly, sometimes risks lives. Well, what if I told you that the reason AI suddenly hallucinates 6 fingers, and the reason medical trials take years, are actually caused by the exact same underlying problem?
So here is the core conflict. When scientists write mathematical theories, whether they're for AI diffusion models or medical probability, they write them for a perfectly smooth, infinite world. But out here in the real world, our physical computers, our actual clinical trials, our databases, they all have to operate in finite, choppy, limited steps.
And that brings us to the hidden math glitch. When you take perfectly continuous, smooth math and force it into a choppy, discrete physical execution, the whole system eventually breaks down. The mathematical guarantees just disappear. You get numerical instabilities in AI, and you get selection biases in medical trials. The continuous ideal and the discrete reality are fundamentally at war. But, as I mentioned earlier, researchers have just published 4 massive breakthroughs that finally build a bridge between the two.
Section 1. Fixing AI's foggy path, stabilizing diffusion. The source material uses this fantastic analogy that I just love. Imagine an AI as a traveler navigating a narrow mountain ridge in incredibly dense fog. The AI has a perfect, continuous map in its head. But because a computer physically has to take choppy, discrete steps, it inevitably takes a tiny step off the exact center of the trail. The quote says it all. Once the traveler steps slightly into the woods, the compass provides wild directions. Because the AI is now in uncalibrated territory, its mathematical compass just goes crazy, sending it careening off a cliff. And that is exactly when your generated image suddenly melts into a glitch. So how do we fix it? Well, researchers have effectively figured out how to add physical wooden guardrails to the math, what mathematicians call Lipschitz continuous projections. Practically, this means that if the AI takes a discrete step slightly off the safe path, it hits this mathematical guardrail and is instantly pushed right back to safety. It completely neutralizes the glitch. Honestly, in the next few years, this simple regularization step is going to make those catastrophic AI hallucinations a thing of the past.
Section 2. Faster drug trials. Anytime valid inference.
Now, that same mathematical friction between smooth theory and choppy reality, it absolutely ruins clinical trials by forcing them into incredibly rigid, pre-planned schedules. In medicine, if you just continuously monitor a drug trial and pick the treatment that looks best at a random early moment, you fall victim to what's called the winner's curse. That early leader might just be a lucky statistical fluke, not a genuinely better drug. To fix this, statisticians developed a brilliant concept called an E-value, which basically acts like a leader's tax. Think of it like a talent show. The more contestants you have and the more often you check the scoreboard, the higher the mathematical tax applied to the current leader's score.
The crucial point here is how this totally changes the game for doctors. Using this anytime valid E-process, they can continuously monitor the talent, the drugs in this case. They apply this leader's tax on the fly, and if a drug still performs incredibly well even after paying the tax, bam, they have found a true champion. They don't have to wait 3 more years for some rigid schedule to finish. They can safely stop the trial immediately. We're talking about saving immense amounts of time, money, and most importantly, getting life-saving drugs to patients way faster.
But discovering the drug in the first place is also incredibly slow, which leads us to a pretty fascinating question. What if we didn't have to redesign new drugs from scratch every single time we wanted to scale up?
Like, why is it that an AI model trained to design small molecules completely fails when asked to design a massive protein?
Section 3. Scaled drug discovery, diffusion on graphons.
To understand why this new concept called diphon is such a game changer, think about architecture versus water. Historically, AI generated molecules a lot like drawing a rigid blueprint, drafting it node by node. If you trained an AI to draw a tiny house, it couldn't suddenly use that knowledge to build a skyscraper, right? The blueprint rules were just too rigid. Diphon changes this whole dynamic by using something called a graphon. Instead of rigid blueprints, it models continuous density fields, much more like fluid thermodynamics. Think about it. The rules for how water flows are exactly the same whether you're filling a tiny cup or a massive reservoir.
And because the AI is now using these continuous fluid equations, researchers can train a model on a tiny, simple 50-node molecule and then instantly ask it to perfectly generate a massive 500-node protein. It works zero shot, right out of the box, no retraining required. This literally shatters a massive bottleneck in computational chemistry and personalized medicine. Section 4. Security checkpoint randomized BH procedure.
So now we arrive at our final breakthrough, and this one solves the absolute chaos of running thousands of simultaneous scientific tests without triggering endless false alarms. Look, in the modern world, whether we're sequencing genes or testing multiomics, we are running thousands of tests at once. Historically, we had different mathematical methods for this, but they absolutely hated working together. They required identical, rigid testing conditions. Now, though, researchers have developed the randomized BH procedure. It's basically a grand mathematical unification that brings all these completely different testing methods under one single umbrella.
Picture a massive airport security checkpoint with dozens of lanes. Some use metal detectors, some use X-rays, some use dogs. In the old math, this messy mix would basically guarantee false alarms. But by injecting a controlled random permutation, literally randomly shuffling the inspectors and the data across the different lanes, the math guarantees that on average, the overall false alarm rate remains perfectly controlled. It allows completely different scientific tests to work together flawlessly.
Section 5. How your life changes the next 1 to 5 years. Okay, so what does this actually mean for you? This is what the next 1 to 5 years will look like thanks to these breakthroughs. By finally smoothing out the friction between continuous theory and discrete physical reality, we are looking at glitch-free, perfectly stable generative AI. We're looking at clinical trials that are significantly cheaper, faster, and more ethical. We'll see the rapid zero-shot discovery of massive new proteins and materials. And ultimately, we are going to have a global testing framework that makes highly personalized medicine incredibly reliable without the constant fear of false discoveries.
So I want to leave you with this final, somewhat provocative thought. For decades, our absolute greatest scientific computing has been held back by the choppy, limited reality of our physical machines. But now that we are successfully building these mathematical guardrails, these taxes, and these fluid blueprints, what impossible problems will we solve once our physical world is finally powered by perfect math? Really think about that. Thank you so much for joining me on this explainer, and I really hope this helped make the invisible glitches of our future a whole lot easier to see.